All right. So today we're going to design the reservoir. And what we need to do is it's sort of a dynamic system because we have 700 gallons per minute coming in, and then we have 1,300 gallons per minute going out, but only 8 hours a day. So what we're going to do is we're going to set up the spreadsheet, and I'm going to start at 8 p.m. because that's the time when we finish irrigating at night. And so I'm just going to fill down 24 hours. Okay. And the first column is going to be our inflow. Q. So flow is often called Q. And that's going to be in gallons per minute. And we're going to run our well pump only as long as we need to. We're not going to run it any longer than we need to because, our well pump runs 24 hours a day, but our sprinkler pump runs 8 hours a day. So we don't have to run the well pump all the time, but we do need to run it longer than the sprinkler pump. So what we do is typically is we'll set up a table with each hour. I'm sure we could figure this out analytically, but a lot of times it's just easier to figure things out in a spreadsheet, not to worry about any theory. So we're just gonna either run our well pump or not run our well pump. So let's say we're going to start it at 2 a.m. and then we would run it until the morning irrigation is finished. So I've got 700 gallons per minute coming in, and my morning irrigation is going to finish at 9 a.m., let's say. So I'll run it from 5 a.m. to 9 a.m. And then I won't run it for some time. But then I'll have to start up again and fill the reservoir before the other pump gets started. So I'm just going to run it for this amount of time. And then my other reservoir is going to turn off at 8 p.m. And the idea is I'll have zero water left at that time. So now I have to figure out my inflow volume. I've got my gallons per minute. And let's just call it V, inflow V. So that would be how much water fills up the reservoir in an hour. So these are hour-long times. And that's going to be equals that. Since this is gallons per minute, I'm going to multiply times 60. And I'm going to multiply times 0.00378 to convert from gallons to meters cubed. Okay. And then I'm going to fill up and down. So that's how much water I'm putting in my reservoir every hour. Now I'm going to do my outflow Q. That's the sprinkler pump in gallons per minute. And remember last night we figured out, or yesterday, we figured out it was about 1,300. And so we're going to run that pump. We're going to start it at 5 a.m. and run it till 9 a.m. Remember, we're trying to avoid evaporation, so we're trying to run it during the cool part of the day. So 4 hours. We're running it 4 hours. So let's get rid of that one. Okay, and so that's just going to be 0 for the other times of the day. And I'm going to run it maybe 4 to 7. So 1300. And 0. Okay, and now I need my outflow cubic meters. So that's going to be the same equation as this one. Looks like I messed up on that. Let's try it again. And now I need my reservoir volume. In cubic meters. So I'm going to start it at 0, so it's not going to have anything in it in the middle of the night. So 0 plus what's coming in there minus what's going out there. And then the only difference in the equation, instead of starting at 0, I'm going to start with whatever I had the last time step. Okay, I'll fill that down. And notice I have negative 68 here. So it looks like I needed to start my um, well pump 1 hour earlier, like 1 a.m. Okay, now I'm at 90. So what I've done here is I've tracked my reservoir volume for time, and I could make a, well, let's not do that yet. And you can see that at the end of the day, I end up with 22. So my reservoir volume is never negative. So I have a good system here. And if I wanted to plot it, I could plot my reservoir volume versus time. Okay, so we can see that this is our reservoir volume versus time. And really, we don't need to know the shape of this curve. All we need to know is that we need about 700 cubic meters in the reservoir.
Hey, Dr. Waller, can you zoom out a bit? My values aren't matching yours.
Okay, glad you brought that up. So you want to look at this equation?
Yeah,
I can't Oh, I can, if I go to formulas, yeah, there's my formula. So 700 gallons a minute times 60 minutes in an hour times 0.00378.
What about the outflow? Are those all 294.84?
So the outflow is the same equation, just going to here. And if we don't show the formulas, they are all 294.84.
Okay. Yeah. Then my reservoir values are wrong then.
Oh, okay. So what you do is you add what's coming in from column C, so
Mhm.
C2, and you subtract E2 at each time step. And for the first time step, it's zero because we're just starting from zero. Remember, we had 22 here at the end of the day. So we're starting
Yeah.
with the end of the day. And then for the second one, now we have this minus this, but we start with what we had before instead of zero. So this is F3. And so we have F2 plus C3 minus E3.
Huh.
Is it not working?
I have the same values up until 467 or 476.
Oh, up until here?
Yeah. And it's the same formula. I
Are
just
you
don't know.
starting? Are you starting your seven? Is your 700 starting here and your
What
1300 starting here at that time of day?
the 700 starts at 2 a.m., right? Oh, 1
No, I
a.m.
have it starting at 1 a.m.
Oh, okay, that might be it then. And it ends at 9?
It ends at 8.
Oh, okay. And then it
And then
starts back up at 1?
it starts back up at 1. And
Okay.
then my 1300 starts at 5 and ends
Okay.
at 8.
Oh, okay, that's where I went wrong.
Okay, so you have the same values now.
What time does the 13 start back up again?
I'm starting it at 4.
Huh.
Are you
Okay.
starting your 700 at 1 and going till 7?
Yeah.
And then you're starting your 1300 at 4 and going till 7.
Yeah. I don't know. I'll rewatch the video and see what I did wrong.
Okay. Well, anyway, this is our amount of water in our reservoir over time. And so now what we can do is, oh, so we're peaking about 650 and um you always want to be a little extra on reservoirs because they can fill with sediment. And so I'm going to have a reservoir volume of 800 just because I don't want to be playing right on the edge of the, overflow or whatever. And I'm also going to give it a little freeboard on top of that. So, so anyway, if I want to have an 800, 800 meter cubed reservoir. And let's say I want to make it 2 meters deep. That means I need a 20 meter by 20 meter reservoir, which is a reasonable size to have on a farm. And I want to have 2 to 1 side slopes. And what that means is the horizontal distance is 2 and the vertical is 1. So in civil engineering, channel design, 2 to 1, it's the opposite of slope, where y is first and x is second. In this case, the x direction is first, the horizontal direction is first, and the vertical direction is second. So I'm going to have 2 to 1 side slopes. And so I'm just going to try to draw it here. So it's going to be sort of flat or flatter than high, if you want to call it that. And I'm going to increase the thickness. Okay. And the midpoint is going to be 20 meters rather than the top or the bottom. If I want to have a 800 cubic meter reservoir, 2 meters deep. So let's put this one on the other side. Okay, and then and like I said, I want a half a meter of freeboard. So, and what that means, that's over the typical water level. So I'm going to have 5 meter by 2.5 meter slopes, meaning this will be 5 meters and this will be 2.5 meters. And then the distance to the 1 meter elevation in the reservoir. So somewhere around there. So it'll be 20 meters in that direction. Okay, so that's my reservoir design. And so it would normally be filled to about here, but every once in a while, the I don't think I'd have much problem with filling in with sediment because I'm pumping out of a well, so I probably wouldn't have to worry about it. But anyway, this would provide me the buffer to use my well pump with my um, centrifugal pump supplying the sprinklers. And I'd also have a 5-to-1 slope at the end, the end that we're looking at, um, for people to walk out. So just in case somebody fell in, you wouldn't want to have 2-to-1 slopes, but at one end you could have a 5-to-1 slope. That's if you were worried about people or animals not being able to get out of the reservoir. And actually, there's probably rules wherever you work on what the reservoir design has to have as far as side slopes and safety as far as walking out and that sort of thing. Any questions? Okay.
No, I'm
So,
good.
okay, great. So next, we are going to design the well pump. Okay, so what we have 700 gallons per minute, and we have let's say the depth is 200 feet. We really don't know what the depth is, but um, so what we have is we have a well casing, and let's just say it's 20 inches, okay? So that's a 20-inch diameter well casing. That means that's the pipe that they put between the well and the outer um, the the soil, not soil, but geologic formation. And so that has some perforated places where the water can get into the well. And then the well pump hangs on another pipe. And let's just say we're hanging our well pump on an 8-inch pipe. Okay. And so let's say that the depth of the well equals 300 feet, and the pump is hanging at 250 feet depth. And the pump is hanging on an 8-inch pipe. So it's 8-inch steel pipe. That's what supports the pump in the well. And then we have a cord going down the 8-inch steel pipe to the submersible pump. So that's a well pump that's hanging on the pipe, and the motor is down in the well, and the cord is bringing it's not a cord, but the electrical is bringing the power down to the pump, which is hanging on the 8-inch steel pipe. So what we're going to do is we're going to look for a 700 gallons per minute, 200-foot head, submersible pump that is hanging at 250 feet. And the thing that we have to say is the well pump, or the well pipe, I'm sorry. That's what let's say it's the pump pipe. That's what the pump is hanging on. It's 8 inches in diameter and it's 250 feet long. And the reason we need to know that is that'll enable us to calculate the friction loss in the pipe that the pump is hanging on. And I've already done the calculation. Actually, I used AI to do that. The friction loss equals about 7 feet of head. So really, we need a pump. And also, I said that the discharge is to the atmosphere because we're just discharging to the reservoir. And so the discharge pressure equals 0. Or I could add like 10 feet if I think I'm going through some fittings. So 0 discharge pressure, but we might have 10 feet of losses in fittings. So really, our pump needs to generate 210 feet of pressure. Okay, so now I'm looking at my AI calcs. Okay, so my power that I need for my pump is my flow rate, Q, times my total dynamic head divided by 3960. That gives you horsepower. So Q in gallons per minute times total dynamic head divided by 3960, and also divided by 0.7, because we're going to assume that the well pump has a 70% efficiency. So let's just put efficiency here, and then we'll and this is the equation we used to use. So even though I got it from AI this morning, this is the actual equation. Okay, so um, so we have 700 times 207 divided by 3960 times efficiency. And that gives me a 52 horsepower pump in the well. So I had 207 feet ahead. Remember, I had my water table was 200. And then I have 7 feet ahead of friction loss. So 207 feet of total dynamic head when the water's flowing, and 700 gallons per minute divided by this conversion factor, 3960 times efficiency, gives me a 52 horsepower pump. Well, if you have a 52 horsepower pump or a calculation of 52 horsepower, then you need a 60 horsepower pump in the well, because they don't make a 52 horsepower pump. And also, I'm forgetting about this, but AI is saying with service factor. So there's also some sort of safety factor. Not sure what it is. But anyway, just to be safe, we're going to use a 60 horsepower pump in the well. And AI points out that this is actually a 36 horsepower of water horsepower. So neglecting the efficiency, we're actually only producing 36 horsepower of water horsepower. So that would be minus this efficiency calculation. Okay. So the next thing you have to do is pick a pump. And honestly, if you're an irrigation engineer, and I'm not saying you're going to be irrigation engineers, most of you are going to be civil engineers, but even if you're a civil engineer, you don't normally pick well pumps. It requires a little more expertise than um, what civil or ag engineers have. So you would call the pump company Gould's, or perhaps use their website to pick out the pump. Uh, like the centrifugal pump, which we did last time, it was quite easy to pick out a pump, and that it's not challenging. But there's many things that can go wrong with well pumps, and so you don't want to be responsible for picking out a well pump. Um, I remember one time our company picked out a submersible pump with like eight. We didn't pick it out. It was from the company, Gould's. But we contracted with a farmer to put in an 18 bowl pump. That means it has 18 bowls stacked on top of each other. It was a 400-foot well, and um, it didn't work out. Not from the fault of anybody at the company or our company, but um, it generally ended in a shouting match. Not us, but the pump installers are often very angry people. I don't know why. It's just the way they are. I think it's because so much can go wrong. Anyway, in this case, the well was crooked. The person who drilled the well. And well drillers are also a little bit sketchy sometimes. They'll come to an area in drought where they're putting in a lot of wells, and then they'll leave. And they often leave things not quite perfect. For instance, this well that this person had put in and left, probably gone back to Texas or something, it was crooked. And so they put down this 18 bowl pump in the well, and it wouldn't go down because the well was crooked. And it was this huge pump. And so who was going to pay for that? That pump guy came down from Canada, and he wasn't going to be left holding the bag. And so, of course, we were a farmers co-op, so we paid for it. You can't get the farmer to pay for it because, I mean, maybe you could, but it was really his fault that the well was crooked. It wasn't his fault. It was the well driller. But anyway, there's a lot of stories of uh, the reason that well pumps don't work. And that's not really directly related to what I'm talking about now, which is that you don't want to be the one to pick out the well pump, because actually I asked AI to pick out a well pump for me and they wouldn't do it. They said consult the distributor. You know, there's electrical wires going down there. There's all sorts of things. So it's a little bit complicated. Anyway, I think what I'm going to do now is I'm going to show some pictures. So for you in your design, you're not going to have to pick out a specific pump. That's what this comes down to. You're just going to have to calculate and I don't know if your design was the same as mine, but you're just going to have to say how many horsepower pump is in the well. And then from that point, you would call the pump company and ask them to spec a pump for you. Okay, so I'm going to try to find this page on the web. Here they are. Here's the gold submersible well pumps. And so this probably directly contradicts what I said before. Because they say you can just buy them from Amazon. This is the actual company that owns Gould's now. It's so here we have 6-inch and larger deep well submersible motors. So these are the motors that hang down in the well and they turn the bowls in the pump. So you have an electrical wire coming down. So that's half the pump, the motor. The motor's down there in the well. And then the other half of the pump is the bowls. And they're not even showing us the bowls, probably because they don't want us to pick them out. Anyway, you should be able to see the top of these pumps. So the motor hangs below the pump. So it turns there's all these bowls in here. It's like the volutes on centrifugal pumps. And then this connection here, that's a threaded connection, and that threads onto the pipe that's dropped into the well that the well pump is hanging on. So that's how that works. Any questions? Hey, are you guys still there?
Yeah, I'm here.
Yes.
Oh, okay, good. So you saw everything. You saw the well pumps and all that?
Yeah, they're pretty
Yes.
nifty looking. I wasn't expecting them to be that big.
Oh, they're really cool. Yeah, I just had a question. What's the difference between the water horsepower and the pump horsepower? So the water horsepower, that's the 36 horsepower. That's what's being delivered to the water. But the pump horsepower is that's what's coming from the motor. So the pump horsepower is 52, and then we increase the pump horsepower to 60 because they don't make a 52, they only make a 60.